Welcome to the third lecture in abstract algebra. The topics that we'll cover in this lecture include lattices, equivalence relations, and the set of integers modulus a given positive integer n. Okay, so we need to cover a few more concepts from number theory before we move on to lattices. An element P and set of positive integers is called prime if P is greater than 1 and the only positive divisors of P are 1 and P itself, a positive integer n, greater than 1, which is not prime, is called composite. All right, so new definition. If A and B are two non-zero integers, then there exists a unique positive integer D which is called the greatest common divisor. Satisfying two properties. First, D divides A and D divides B. And second, if some other number E divides A and also divides B, then this number divides D. So the first property says that the number D, the integer D, is a common divisor of both A and B. And the second property says that it is the largest common divisor of A and B. So we call it the greatest common divisor. Now, the requirement that A and B be non-zero is necessary to ensure the uniqueness of the positive integer D, because any integer can divide the number 0. Now, I will use functional notation to denote the greatest common divisor of two elements, A and B. And this is our unique element D, or integer D, positive integer D. Two things to point out immediately. Since any divisor of the integer n is also a divisor of negative n, if A and B are not both 0, then the greatest common divisor of two non-zero integers, well, one of them not equal to 0, A and B, is the greatest common divisor of the absolute value of the integers A and B. So now we need to address the case where one of the integers is 0. And by convention, the greatest common divisor of 0 in any integer n is the absolute value of that integer n. And this is because n certainly divides itself, and any integer divides 0, and so n certainly divides 0. And so in the case that we consider the greatest common divisor of two integers, one of which is 0, we say that the greatest common divisor is the integer n, well, the absolute value of the integer n. Okay? So new definition. Once again, if a and b are two non-zero integers, then there exists a unique positive integer L, which is called the least common multiple satisfying two properties. First, A divides L and B divides L. And so they are both, L is a multiple of both A and B, or is a common multiple of A and B. 2, if both A and B divide some number m, then L divides this number m. So the first property tells us, again, that the positive integer L is a common multiple of A and B. And the second property tells us that it is the smallest of the common multiples of A and B. All right? Now, I will use functional notation to denote the least common multiple of two elements, two non-zero elements, A and B as well. So let's look at an example. We have defined the greatest common divisor and least common multiple for a pair of non-zero integers, but it will work for 3 or more positive, non-negative, or rather non-zero integers as well. So let's find the greatest common divisor and least common multiple of the numbers 3, 9, and 12. Now, a good technique is to write the numbers as factored into primes. So 3 is a prime number. 9 is 3 squared. And 12 is 2 squared times 3 squared. So the greatest common divisor of 3, 9, and 12 is the largest positive integer that divides all three numbers, 3, 9, and 12. Now, 1 certainly divides these numbers, and the number 3 also divides these numbers. But 1 divides 3, and so 3 is the greatest common divisor of 3, 9, and 12. And notice that in each of the terms where we factored them into primes, 3 is common to all three numbers. Now, the least common multiple of 3, 9, and 12 is the smallest integer that is a multiple of 3, 9, and 12. And so it has to be a multiple of 2 squared, since that is one of the multiples of, or one of the factors of 12. And it must be a multiple of, well, 2 squared times 3, rather, not 3 squared. 3 squared, as that is a factor in the integer 9. So notice that the least common multiple must include each of the factors that are common in the prime factorization of these three numbers. So 2 squared times 3 squared is 4 times 9, which is 36. So the greatest common divisor of 3, 9, and 12 is 3. That is the largest positive integer that divides all three numbers. And the least common multiple of 3, 9, and 12 is the smallest positive integer that is a multiple of each of these numbers. And again, it must include as its factors, as its prime factors, those that are common or that appear in each of the factorization of the three numbers. So it has to include the 2 squared, and it has to include the 3 squared. And so 36 is in fact a common multiple of 3, 9, and 12, and it is the smallest multiple of 3, 9, and 12. All right? So now we're ready to move on. Let the set A be a subset of the poset S with some relation R, some partial ordering, an element U in the set S is an upper bound of the subset A if for every element A in the set A we have that A is related to U. Now notice that the element U need not be in the set A itself, but it needs to be in the underlying set in the poset. And if it is true that for every element in the set A that element is related to this element U, then that element U is an upper bound. So often a given subset will have multiple upper bounds. So we look for the smallest of those upper bounds and call it the least upper bound, or supremum. So the element U sub naught in the set S is the least upper bound or supremum of the set A if U sub naught is an upper bound of the set A, and U sub naught is related to Z, where Z is an upper bound of the set A. So this is somewhat analogous to the least common multiple for two numbers, in that the least upper bound, or the least upper bound or supremum, U sub naught, must satisfy two conditions. First, it must be an upper bound of the set A, and it must be the smallest upper bound. So it must be related to Z, where Z is any upper bound of A. Okay? So next, once again, let A be a subset of a poset. An element L in the set S is a lower bound for the set A if for every element A in the set A in the set A, we have that L is related to that element A. So once again, the element L is in the underlying set in the poset and need not necessarily be in the set A. But if it is true that for every element in the set A, that element L is related to A, then that element L is a lower bound for the subset A. Once again, a given subset can have multiple lower bounds. There can be many lower bounds. So we look for the greatest of these, and we call this the greatest lower bound. So the element L sub naught is the least, or correction, the greatest lower bound or infimum of the subset A if L sub naught is a lower bound for A, and Z is related to L sub naught, where Z is a lower bound. So analogous to the greatest common divisor, we have the greatest lower bound or infimum of a subset, where we have an element in the underlying set of the poset that must satisfy two conditions. One, it must be a lower bound for the subset A, and it must be the greatest of those lower bounds, of the possible lower bounds for the set A. So the element L sub naught is a lower bound for A, which means that for every element in A, L is related to A. And for any other lower bound, Z, for the subset A, Z is related to L sub naught. So it is the greatest lower bound, and we call it the infimum. Okay? So we'll look at it at an example again. So consider the set A consisting of the numbers 3, 9, and 12 as a subset of the poset consisting of the positive integers with the relation divides. And we will find the infimum and supremum of the subset A. Okay, so the infimum of the set A is the greatest lower bound of the set A. And here the relation is divides. So we're looking for the greatest positive integer which divides 3, 9, and 12. And so as we know, this is the greatest common divisor of 3, 9, and 12, which we know to be 3. Now the supremum of the subset A is the smallest upper bound of the subset A. And so again, we're dealing with positive integers and the relation divides. So we are looking for the smallest multiple of 3, 9, and 12, because we're looking for the smallest number for which it is true, positive integer for which it is true, that 3, 9, and 12 divides this upper bound. And so we are looking for the least common multiple of 3, 9, and 12, which we know to be 36. So notice once again that the infimum and supremum must be elements that exist in the underlying set, in the poset, but not necessarily the set A. Now, the set A does include its infimum, but does not include its supremum. Okay?